transient conduction, okay, is chapter 5, okay? And we'll just be doing the lump capacitance method, okay, which deals with 5.1 through 5.3. Chapter 5 is all transient conduction. 5.1 to 5.3 is the lump capacitance method, okay? So we have, in this transient conduction, that means temperature is varying with time. So that means we have the energy stored term is changing, right? Which then means inside that stored term we can put rho v c t, so we can change that to our and temperatures changing with time, okay? So what's happening is we have a change in boundary conditions, and you see that here. So, maybe you have a sphere, okay, and then all of a sudden you have surface convection. So maybe you drop it into a bucket of hot oil, okay, or the sphere is hot and you drop that hot sphere into a bucket of cool oil. By doing that, you're changing the convection coefficient right around that sphere and the temperature, P infinity, okay? So you're changing those two parameters. Maybe you have all of a sudden surface radiation. You have some heat lamps or something like that that you all of a sudden put on this sphere, okay? Maybe you have a surface temperature change. So maybe you're blowing steam over it, so that'll keep it at the saturation temperature on the surface. Or maybe you have a heat flux that's constant. So maybe you have a surface heater on it. Or maybe it's a internal energy generation all of a sudden inside. So all of a sudden you have a change where now all of a sudden a chemical reaction is occurring inside your system, okay, or a nuclear waste or something like that, where all of a sudden it is, okay. So when these transient conduction problems, we have the case of lump capacitance, which we will do, okay. We have some exact solutions, which are limited, so we're not going to cover that, okay. So there are, those equations are good, but they have to meet the requirements for those solutions, okay. So it's like there's equations for, say, an infinite solid. So if you had like a hot probe you stuck in oil, or into soil, let's say, or a thermal energy that you're doing, so some kind of thermal energy pipes or something that you have in the ground, you can think of the soil as an infinite solid. So those equations would work in that case. Okay, so they have exact solutions for these equations, but you have to have certain conditions so that they could solve the equation. All right. The other way, a very popular way these days, is finite difference method. Okay, so that's where, anytime you have this, say, dt, you have a numerical approximation for that change in temperature versus change in time. Or in finite difference, it's, you might grid something. So you might do this in FEA class, which you might not have had yet, where you have a grid, right? But instead, in this, you would apply the COE, or the heat equation, to each of those points, okay, and solve for each of that grid or mesh that you create at each of those points would have the finite difference method to it for numerical approximation of different equations. So in this, it would be the heat equation, heat transfer would be the heat equation, or the COE, and fluids, it would be the Navier or Stokes equation, and in FEA and solid mechanics might be Newton's second law. So you're just taking any of those equations that have a derivative or a partial derivative and applying a numerical approximation for that derivative. Okay. And that's what happens in NX. So NX has equations or solvers for heat transfer in it. Same with SolidWorks. Any of those have these equations that numerically approximate these equations. And so then you can do solvers for different geometries in that, different conditions. So we're going to be looking at lump capacitance. All right, so lump capacitance has a major assumption that goes with it, okay, to make it valid, okay, so that we can use it. And that's the assumption of a spatially uniform temperature. So if we had a sphere, okay, it's saying the temperature here is the same as here, is the same as here. Okay, the temperature is always the same temperature, and it's only changes with time. Okay, so if we, had this hot sphere and dumped it in a cold oil, you have this convection coming off of this, our boundary around it, and we can look at the temperature inside our sphere is always the same. Okay. So that's the assumption that goes with it. But why is this assumption never fully realized in practice? So if you take this example I'm giving of it's a hot, maybe it's a stainless steel ball or steel bearing or something like that that's very hot, and we dump it in oil that's at room temperature. How would this look like inside this sphere, the temperature profile? Would it, in that instant you dumped it in the oil, would the temperature here, here, and here be exactly the same?
No.
So what would be hotter, what would be colder?
The center would be hotter than the outside.
Yeah, so we have, in that instant, in that very, quick instant there, you have the temperatures. We have, if it's cold oil, then it's going to cool the outer surface faster than that inner, right? And if we're just looking in the radial direction, we could think of it like these, with these different constant temperature lines, make it look like an onion. And we have that change, right? For it to actually not ever have that temperature change inside, that would be where the thermal conductivity is infinite, okay? Right? It has that thermal energy moving through conduction so fast because it's infinite that there's no temperature change through that sphere, right? Well, we're going to still be able to make that assumption in some cases where it's still relatively high, because right now we have this conduction that's going through here, right? That's Q conduction, but we have convection on the outside. Well, we're going to be looking at it as a ratio of conduction versus convection, or whatever's happening on the outside surface, inside. And if the inside, the conduction is happening very rapidly compared to what's happening on that outside surface, then we can neglect the influence that the conduction would play on the temperature change with time, right? And assume it's basically like an infinite thermal conductivity. And we'll talk about that in a second about when we can say that, okay? All right, so we're going to start off with the general lumped capacitance method, which you see a schematic for it. So here's our schematic. So we're going to say we have this plane wall, and all of a sudden we're going to do a whole bunch of stuff to it. We're going to have a surface heat flux right here. We're going to all of a sudden apply a surface heat flux. We're going to apply radiation. We're going to apply convection. And we're going to apply energy generated. Okay, so we just put 4 different things happening on this plane wall all of a sudden, right? It was first was at an all initial temperature, and then boom, we said radiation, convection, surface heat flux, energy generated. Okay. We said go big or go home, right? And we have an area that goes with each of them, just to keep it, we're not simplifying, we're keeping it very general. So this area, surface area, goes with the heat flux. There's one surface area with conduction. There's another with radiation. That's what you see here. That's why you have 3 surface areas. They're keeping it, different. So maybe you have radiation on this wall on the right and heat flux on the left wall. So that could potentially have 2 different surface areas. So it's general. All right. So in that case, if we have that, we can start with our COE, right? And we have our energy stored, and then we have E in, E out, energy generated, right? So we look at our schematic, what's in, what's out. We have our heat flux going in, radiation out, convection out, and our energy generated. Okay. So heat in is our heat flux, out convection, out radiation, and we have our energy generated that's happening, that we all of a sudden have applied, right? All right, so how would we, if we had this situation that you see in the schematic, and now with this equation right here, okay, this equation, how would you solve this equation? We want to know the temperature of this plane wall after some amount of time. So these conditions are happening here, and we want to know the temperature after some amount of time while the temperature is changing with time. So it's not steady state, it's during that transient process. How would we solve this equation? Any ideas?
You'd have to separate the dT to one side, or the temperature change on the left side, and the change in time on the right side, then integrate.
Well, we'll do that for some of these, but you actually can't do this with this equation. I mean, they show it with HR here, but in reality, this has the radiation inside this radiation HR has temperature terms that are squared root, and if you take radiation with kind of removing it being this parameter, because that parameter depends upon the temperature, you have this T to the 4th, okay? And because radiation has the T to the 4th, it's buried inside this HR. You can't integrate because you have this temperature here, and then you have this temperature T to the 4th. It's not a situation where we can. So we'll show the situations when we simplify. If we cross some of these terms off, we can do that, integrate. But if we have radiation, which has temperature to the 4th, and any of these other terms, we can't solve it without numerically solving it. And basically, we would have delta T over delta T for this. And we'd have to march in time. So if we looked at time versus temperature, say we're at some initial value. So we would have, march through time and solve, maybe in Excel, solve for this one, and this one, and this one, and this one, and kind of march through, okay? We can't jump from here to here because we would have this delta T over delta T, which is kind of a slope. So if we approximate it just with one step, that would be solving from here to here. Okay, and you see it's not a linear, it's nonlinear. So you have to do these many you have to do a step-based solution where you march through time. Okay, so that's a numerical method. So it'd have to be solved numerically. So, and that's due to the really radiation in any other term. Okay. Questions on that? All right. So that means radiation's kind of the pain, right? So what happens if we say, okay, let's take special cases. Let's neglect radiation. Okay, so now that means we have, or let's say include. Let's do that. That's a better one. Include convection, heat flux, and energy generated, but neglect radiation. Okay. So now, if we do that, we go back to this equation. We can cancel off this term and say we're neglecting it. Neglect. And that means now we have still this term, this one, and this one, and we can do what was stated, is we can move the dt over and do a substitution for theta. Okay, so then temperature is d theta over dt. Okay, and when we do that now with some more substitutions, that's all you see kind of here is they're substituting theta, and then they substituting in theta prime, and theta prime is the same, you know, its change is the same as dt because this is all constants here. So it's just a lot of substitutions to get a nice form that we have seen in our math classes that can actually be integrated. Okay, so we see this nice form here, integrate it, and then back substitute all our parameters, especially theta prime and theta, and we get our equation that has time, right, and then temperature. Okay, so this is time and temperature. It relates. So if we know time, we can solve for the temperature. If we know temperature, we can solve for the time. Okay. You know, we have to plug in A and B, right? Parameters that you see here, A and B. Okay. So the most important thing you see in this equation is that it's neglecting radiation. You can actually still use this equation if some of these other terms are neglected also, but you have to have radiation neglected. So if energy generated, let's say, is neglected and radiation, this just becomes zero. And same equation, because same equation to substitute and integrate. Okay. Same with heat flux, let's say, or convection. So any of these, as long as radiation is neglected, this equation works for those other cases too. All right, if we look at this equation, so this equation that we see above right here, what does this reduce to when steady state is approached? So can we, you know, looking at this equation, is there any kind of cancelizations that we can make when we're going steady state? What happens with time when we go to steady state?
To be the exponent, it's going to go to 0.
Yeah, so the exponent goes to 0 because time, right, goes to infinity, right? As time goes to infinity, we have a negative, so it ends up being negative infinity. Okay, so that goes basically to 0 here. Okay, we still have this part, right? And this one goes to 0 also when time goes to infinity. So we're just left with kind of this part here. Okay. And we'll substitute in A and B, and we'll have our equation for steady state, right? How else, you know, not using this equation, get rid of these cancels. It'll let me. There it goes. All right, so how else, so we're not using this equation above, right? But how else would we get a steady state solution for the same case? And so we're looking at this equation right here. We're neglecting radiation. How else would we solve this problem if we're just looking for the steady state solution?
dt goes to is to 0.
Yeah, so if we're just looking for the steady state, this goes to 0, right? And we're gonna end up having just this component, and this component related, right? Well, that's the same thing that actually, not get that crossed, but that's the same thing you're gonna be left with when you're left with what we did with the simplification for t going to infinity of that equation. That's what's gonna end up resulting when you move things around, okay? All right, so let's make another case that's even simpler than the last one. So this case, we have, you know, convection's dominating radiation. So that means we can neglect radiation. So include convection, neglect radiation, which we did on the last one, but we're also going to neglect energy generated and the heat flux. Okay, so we go back to our equation here. We neglected radiation, but we're also going to neglect energy generated and our heat flux, right? So then all we're left with is convection, okay? So that's the two terms we're left with, this one, and you see it here. And then moving dt around with our substitution, okay? That means we can now integrate it, so we get our equation you see here, okay? And that relates time and temperature, okay? So inside of it, it has a parameter. This parameter, which can also be thought of as a thermal time constant. All right, thermal time constant, it, you know, just like you saw in, you know, electrical conditions where you have a resistance and a capacitor where you could have a charging circuit, same kind of things happening in this transient thermal cycle. You have a thermal resistance, so in electrical you have a resistor and a capacitor. Well, our equivalence for resistance is our thermal resistance, which is convection times its surface area and 1 over it, okay? So it's the convection resistance. And then the thermal capacitance, which is basically density, volume times specific heat, which is mass times specific heat. So that's kind of like the energy it can store, right? Relate the thermal time constant. So if you change the convection coefficient or you change the material of that you're looking at, it'll change, one will change the resistance, one would change the capacitance, so they would change that thermal time constant. And as you change your thermal time constant, it changes how that curve looks. Okay, because it's showing 0 to 1. That's because this equation, if you're just looking at the exponential with time over the time constant, that just results in a number that's between 0 and 1. This is seconds and this is seconds, and it cancels. So it's just a ratio of 0 to 1, which is what this is, a ratio of 0 to 1 in delta T's. Okay, so it's all kind of non-dimensional when you look at it that way. All right, so then the other equation that comes with this one is the change in thermal energy storage. So we can just kind of look at the energy change over the whole thing at any given time of the stored energy inside our system. So if we were looking at the sphere, it's the energy stored inside that sphere, how it's changing, which is just the heat out, right? This would be, say, convection out in this problem, which is the energy out. So you'd have energy out is convection, but the temperature, which is theta in this case, which is T minus T infinity, is changing with time. So we have to integrate, okay? So if we integrate theta, which we can just get theta from this equation, rearranging this equation just for theta and integrate it, we end up getting this is related to this, okay? Which shows time and energy, okay? Energy stored. Okay, so this, if you look at this equation, again, we can see this part is just from 0 to 1. Okay, and this part is actually just the total energy that could possibly be stored. So if, again, we look at this problem, this equation, and as t goes to infinity, this goes to 0 as t goes to infinity. So as we go to steady state, we're just left with energy stored equal to this term. Okay, so that is the max kind of energy that can be stored: density, volume, specific heat, T minus T initial minus T infinity. That's our maximum that can be stored. Okay, that's just basically change in internal energy, right? Now, for any time in between that, we're kind of that ratio of to that max. Okay. All right, so now we're going to take another one, and this time we have negligible convection and source terms. So that means we're going to include radiation, neglect convection, energy generated, and heat flux, surface heat flux. All right, so that means we go back to our equation here. And we're not neglecting this radiation term anymore. We're neglecting energy generated, convection, surface heat flux. So now we just have our equation here and here. Okay. And that's what you see right here from the COE, what we're including and neglecting. And now we can move dt over and integrate this equation, and we get this nice small equation 5.18. Right? Fun one to write down, fun one to put in the calculator, and a fun one to get our answer. Right? So we see this one, and it relates time and temperature. Time's much easier to solve in this one than temperature. So if you had a temperature that you're looking at what time that occurred with this pure radiation, you just put your temperature in here, the other surrounding and initial temperatures, and then you solve for time. Now, if you had a time and you wanted a temperature, this problem now requires some iteration where you guess and check and move and iterate through. Okay. Questions so far? All right. Now, when can we use this? We got to check the Biot number, okay, to make sure our lump capacitance is valid, that we're with our big assumption of that uniform, spatially uniform temperature distribution that we're assuming. And how we check that with the lump capacitance, okay, or with the Biot number, sorry. It's a dimensionless parameter. So, you know, in fluids, you had Reynolds number, right? And all these dimensionless parameters do is, you know, they obviously they don't have a dimension to it, but then they also are comparing things. You know, they're a ratio of something in the numerator versus denominator. They're a ratio of two things, and when a parameter is low or high, you're able to tell something, right? With Reynolds number, you have, you know, laminar versus turbulent. Tells you a ratio of what's going on inside that dictates kind of what that flow happening. Biot number is telling us things about, you know, whether we can use the lump capacitance method. And it's showing us, first we'll start with the definition. It has convection, characteristic length over thermal conductivity. And this is of the solid. It's not of the fluid that's around it. So if we're looking at the sphere, right, it's kind of looking at that the ratio of kind of like the conduction here and the ratio of convection here, right? So the thermal conductivity is of the solid inside. So physical interpretation, if we move some of these parameters around to make this more into a resistance, thermal resistances, we have L over K surface area, A. So that would be our resistance of our conduction. And if we do 1 over HA, that's resistance of convection. So it's a dimensionless parameter that shows a ratio of conduction over convection. Okay, if it's very low, that means the resistance of convection is much higher than the resistance of conduction. If it's very high, the resistance of conduction is much higher than the resistance of convection. Okay, and what this means for the lump capacitance is we want it much less than 1. So we'll kind of use a parameter of less than 0.1. Right? We always want to check the Biot number, and we always want to specify it, right? Because as the Biot number gets larger and larger, the accuracy gets less, right? If it's much less than 0.1, maybe it's 0.0001, you're going to have a very accurate analysis. Now, if it's 0.09, you're going to, you know, your accuracy is going to diminish as it gets higher and higher. Okay, so we want to comment and check our Biot number to say lump capacitance, kind of comment on that too. So if it wasn't valid, we would have to do one of the other techniques. Maybe still one of the exact solution applies for our system. Or if not, that means we're doing a finite difference method. We're using NX, or we're doing it by hand, or some method where we have to use a solution that takes into account the temperature change inside the system for conduction. It's basically influencing the time versus the temperature versus time. Okay. All right, so let's do some examples. 5.13. Thermal energy storage systems commonly involve a packed bed of solid spheres through which a hot gas flows if the system is being charged, or a cold gas if it is being discharged. In a charging process, heat transfer in the hot gases increases thermal energy stored within the colder spheres. During discharge, the stored energy decreases as heat is transferred from the warmer spheres to the cooler gas. And then they show you this schematic here. And it says, consider a packed bed of 75 millimeter diameter aluminum spheres, gives us density, specific heat, thermal conductivity, and a charging process for which gas enters the storage unit. So the gas temperature gas enters the storage unit at a temperature 300 degrees Celsius. If the initial temperature of the spheres is 25 degrees Celsius and the convection coefficient 75 watts per meter squared Kelvin, how long does it take a sphere near the inlet of the system to accumulate 90% of the maximum possible thermal energy? What is the corresponding temperature at the center of the sphere? And is there any advantage to using copper instead of aluminum? All right, so we see our system. So they have this packed bed of spheres. There's a whole mess of them here, right? They're all over, okay? So the spheres are initially at a temperature of 25 degrees Celsius, and we have hot gas flowing over it. It asks about the sphere at the inlet. So, maybe right here, we're looking at a sphere, okay? So the sphere is initially at a temperature 25. We have all the properties for it, diameter, and it asks us first off what time required for the sphere at inlet to acquire 90% of the maximum possible thermal energy. Okay. All right. Before even starting that, what terms in kind of the COE on this sphere are we including? What are we neglecting? So we have heat flux, we have convection, there's radiation, there's energy generated. What are we including? What are we neglecting?
Conduction.
Which one we're including or not including? I'm still not catching it, sorry. So what are we, neglect conduction, okay? So that one, to neglect the conduction means we're gonna check the Biot number, okay? So we're gonna have to check the Biot number, okay? All right. What else can we neglect, or what do we have? Is there energy generated on the sphere? Inside the sphere? So we're flowing hot gases, no generation, okay? So we're flowing hot gases over it. So there's no generation. Is there a surface heat flux that we're applying to the sphere? What's being applied? What type of heat transfer is happening on the sphere?
Convection.
We have convection, okay? We have this hot gas that's going over it, right? So we have convection. All right, so we have a convection, and we're gonna neglect generation, heat flux, and we don't have an applied surface heat flux. That's where we're like putting a heater on it directly, okay? And we're going to neglect radiation, okay? All right, so they didn't give us any parameters for radiation, so that's a big hint in book problems. In practicality, what you want to do is check is check the conduction versus convection. So where H is much greater than HR. Okay, HR, you can find the equation for that in chapter 1. It kind of changes the radiation equation that has temperature of the fourth to a linear equation where we can kind of utilize it for HR. So that would tell us to neglect radiation if convection's the dominating versus radiation. All right, so we have include convection, neglect energy generated, heat flux, and radiation. Okay, so if we go to this includes radiation. No, we have convection, neglect radiation, energy generated, heat flux. Okay, so this is our slide that has done that to the conservation energy. Okay, so we have these equations. We have this one down here, and we have this one here. Okay, so this one relates time and temperature, this one time and energy stored. Okay, so we have those two equations. Okay, so we need to check the Biot number, which I'll show that in a second. First, it'll be that, but also before I switch to the next slide, what equation do we think we're looking for? First off, time required for the sphere at the end to acquire 90% of the maximum possible thermal energy. So we're here. Do we use this top equation or this bottom one then?
The bottom one?
Yeah, so the bottom one deals with time and energy stored. So we got to figure out, though it says 90% of the maximum. So we got to figure out how to do 90%, but we're going to use the bottom one, okay? All right, so first off, we'll check the Biot number, right, which is HL characteristic over thermal conductivity of the solid. All right, we have H, we have K, and for a sphere, the characteristic length reduced to radius divided by 3. So LC is really just volume over surface area. For any geometry, it's this, that. For a sphere, it reduces to radius divided by 3. So when we do that, plug in our values, we see here, we're much less than 1.004, okay? So if we have that, okay, and so we're good here, so we can use lump capacitance. Boom, all right, we're good. All right, so then we have this 90% of the maximum possible thermal energy. We know what equation we're gonna use, okay, and that one, we have what we, and it's already kind of showing the big kind of movement in the equation, is it's 90% of the maximum possible. If you remember when I was going through this equation, this right here is the term that shows the maximum possible, okay? Because if you take time to infinity, that's what you're left with. So if you had an infinite charging of that sphere, that's the energy stored that you would get. So we're looking for 90% of that, right? So we just move this over and relate it to 0.9. Okay, and that's what's done here. So we just move that term over, and now that ratio is 0.9, and then you're just left with this. So now we have 90%. So we have this whole term as 0.9, and now we just need to solve for time and get our thermal time constant. Thermal time constant just lumps all our parameters together, so we can easily get that solved. And then time, we just got to rearrange our equation using natural log for time, and we get 984 seconds. All right, the next part asks us for the time, so it's now the time that corresponds, you know, or sorry, the corresponding center temperature at that time, okay, of 90% maximum possible thermal energy. Okay, so we go over here, we have our two equations, we just use this one. So we're gonna use probably this top one, right? We have a time and we want a temperature. Okay. All right, so if we do that, you know, let's go back to that equation because they've already rearranged it. We have this time, we have a thermal time constant, and then we need this temperature. You know, we have T infinity, we have T initial, so we're just solving it for that temperature. And that's what you see here. They've already rearranged and substituted a little bit of this for this equation. Okay, so we get 272.5. The last kind of thing they ask some questions about is more kind of looking at the parameters. It was like, what would happen if you had copper instead of aluminum? And really, you're just looking at the properties, right? It would be dealing with this density specific heat. Okay, so when energy is stored, how long would it take? So kind of looking at those properties and changing them out. Okay. The other question is time required with increasing distance from the bed inlet. Okay, so the problem asked time required at the inlet. So we looked at a sphere here. Well, there's also spheres at the outlet. So we have issues with all those spheres in between, right? So it's going to have a delayed for that sphere near the outlet, right? We might have to look at kind of section by section or some other maybe numerical or something in that analysis to get maybe time for that outlet sphere. All right. So another question. We have 5.19. A plane wall of a furnace is fabricated from plain carbon steel. So you have a K, density, C, right? So you have properties for the carbon steel, and is of thickness L, which is 15 millimeters. To protect it from the corrosive effects of the furnace combustion gases, one surface of the wall is coated with a thin ceramic film that for a unit surface area has a thermal resistance 0.01 meters squared K per watt. The opposite surface is well insulated from the surroundings. At furnace startup, the wall is at an initial temperature of 300 Kelvin, and the combustion gases at T infinity of 1300 Kelvin enter the furnace, providing a convection coefficient of 30 watts per meter squared Kelvin at the ceramic film. Assuming the film to have negligible thermal capacitance, how long will it take for the inner surface of the steel to achieve a temperature of 1000 Kelvin? What is the temperature of the exposed surface of the ceramic film at this time? All right, so they gave us also in this problem this schematic. So we see we have all of a sudden these hot furnace gases, okay? We have this carbon steel wall that's insulated on the right. We want a temperature right there of how long it takes for that inside surface to be 1000. Okay, so that's going to be a given. Okay. So this film, though, we have T infinity was given. Okay. H was given. And TSI was a given. This wasn't given. This is given. We have all our properties given to us. Okay. And we have the resistance. Okay. All right. So you see the schematic down here. They're first off looking for time required for the surface of the wall to reach prescribed temperature, and B, the corresponding value of coating surface temperature. All right, so in this case, what are we including? What are we excluding? So again, we have the situation of convection only, right? Okay, so we're convection only, which is this case here. Okay, and they're asking us about time and temperature. Okay, so we're going to be using this one. Okay. So convection only, and we need to check the Biot number. Okay. All right. So there's one key thing they told. I mean, there's a bunch of key things they told us, but one of the unique things in this one is we have this film, right? That's right here with the resistance, and the schematics here. And they told us assume the film has negligible thermal capacitance. Okay, so that means we're neglecting the part of the film is energy stored term. So if we thought of energy stored dt, and we put our boundary around the wall and the film, that's going to have the energy stored, you know, in the film, plus the energy stored in the wall, dt, and we're neglecting this part, right, which would have been a rho v c dt dt of the film. We're just going to have the rho v c dt dt of the wall. Okay, so this is the part we're neglecting. Okay. All right, so what that means, if we neglect the energy stored in the film, we can think about the film automatically going to steady state. If there's no energy stored into it, it's like a thin wall. It's like a surface, right, that we dealt with. You know, when we do COE on a surface, it's like there's no energy stored in it, right? Well, if we do that, we can set up a thermal circuit for just the film. So that means there's resistance of convection and then our film resistance. Okay, and then this gets us to that temperature that we have at the inner surface of the wall. So because we have this one and we have this one, so we need to relate from here to here on our heat of what's going into that steel wall. Okay. All right, so we need to check Biot numbers, so let's start there. All right, Biot number usually looks like this, and you can see in this one the H is changed to a U. And that's because we have that thermal circuit. Because we're looking at the steel wall, but we have a film between it. Okay, so that means we need to get what this wall is experiencing in kind of a convection term, not the film. And that's where we use the thermal circuit. We get kind of an overall kind of convection coefficient, this capital U. So if we think about this for a plain wall, it looks 1 over U is equal to R total, which is equal to R convection. And this is double prime because the surface area is the same with a plain wall. And then we have add our film. Okay. So and that comes from the first part of chapter 3 in our slides, this overall convection coefficient. It was there on the slides for the plane wall, for cylinder, and spherical. All right, so calculate U, which is the overall kind of convection coefficient going into the wall, instead of H, which is the convection coefficient going into the film. Okay, so we calculate this capital U, adding those resistors, and we get 23.1, which is different than the 30 that the film feels, right? Because there's the resistance of the ceramic film itself that's getting applied. So when we put that 23 there, we still get a number that's much less than 0.1, so we're good, okay? We are awesome. All right, so then we get we need to solve for knowing temperature, right? When we go back, so that was the difficult part because we got the overall convection coefficient. Knowing temperature, we need time. Okay, so we know temperature, we know T infinity, T initial, T infinity, and we need time. All right, so we can solve for the time constant or these parameters, and we just have to put in capital U for H there. Okay, and that's what you see here. Time constant is being it's being plugged in, and the values are there. So we rearrange this equation right here for time. Okay, and that's where the natural log comes in. We're just rearranging and solve for the time with all the parameters now. Plug in, chug, and we get 2,642 seconds or 0.734 hours. Okay, so that was the time required for the surface of the wall to reach the prescribed temperature. So that was PSI equal to 1,000 Kelvin. So that was the time to get to that temperature. Okay, and then they ask the corresponding value of the coating surface temperature. So that means they're now asking for TSO. So if we know TSI, we know T infinity, we can utilize our thermal circuit right here for the outside surface of the film's temperature, because it's just kind of at steady state, the film. It doesn't matter. There's no energy stored in it. And that's what you see here. You're just using the thermal circuit. So if we had T infinity, TSI is resistance convection plus the resistance of the film. We have this, right? Because that's what Q is equal to. They're using, we could also use they use the equation of knowing this delta T and this delta T and relating it. Okay, I just used this one to this one and then this one to this one, set those equal. And we needed just this. We have this, and this. So it's just using that equation, we get 1069 Kelvin. And how does the coating affect the thermal time constant? This is where we can play with, remove the coating. Just remove that resistor and resolve with just the convection right directly on the steel wall and see how everything plays out. Okay. Any questions? All right, so that's it for today. I have a couple couple problems to do next class. It'll take us a max of 30 minutes, maybe shorter, probably shorter. You know, once you know the direction to solve these problems, they don't take long. So shouldn't take very long at all. Maybe 15 minutes, max of 20 or max of 30. All right. So then you have a good rest of your day and week. And we'll meet again on Wednesday, if there's any questions.
Thank you.
Thanks.
Doctor, we don't have
Yep.
class on Monday?
Huh? Or sorry, we'll meet again on Monday. Sorry, I misspoke.
Okay, just a question. Can you share more details about the exam, how it's going to be, the format? Is it going to be, I mean, is it going to be live or how it's going to run? How it's going to be?
I mean, it'll be online where you get all day to 1 day to do it, but it's 2 days or 2 hours to solve, and you'll have a problem from chapter 2, chapter 3. You might have 2 problems, and then there'll be a chapter 5 problem.
Okay, can we get like a cheat sheet, or there's nothing to put on the desk?
You can create one yourself,
Okay,
or use a book if you have a printed book, or tabbed in a PDF, or whatever you want to do on the to go to what you need.
okay. Is there like an honor lock or anything?
Is there what?
Honor lock or like a...
Well, block? No.
Okay,
It's you just have the limit of 2 hours. So
okay.
to submit all your work too. So all right.
Thank you.
Yeah, I'll talk more about it the next class too.
Okay, thank you. Appreciate it.
Yep.